Okay, so now we talk about, I introduce you a linked retrieval to try to improve the result from the Boolean model. Okay, so here we wish to return the documents according to their score relevant to your query, not just the exact match. Maybe you can perform some partial match. So we will assign a score for each document, with respect to the query, or maybe like from the score, maybe from 0 to 1. Okay, assigned to each document. So the score can be used to reflect how well documents and the query match. Okay, so again, we take the incident matrix. Okay, we call this we use for the binary retrieval model. And now, if we will try to turn it into a vector retrieval model, here now we use called a term frequency. A term frequency matrix like this. Okay, so you see, it's not only 0 and 1. Now we show some the frequency of the terms. Okay. For example, the first frame it has 157. This means the anthem, this word, appear 157 times in the first frame. And this is for the second frame. Anthem appears 73 times. Okay, so now we use the term frequency to represent the document and the term relation. Okay, the traditional method framework is called a bag-of-words model. A bag-of-words model means you can treat the document as a bag, and you count how many words appear in this bag. And in this model, bag-of-words model, we don't mind about the order of these words. We just count how many times the word appeared. For example, John is quicker than Mary as the first sentence, and Mary is quicker than John is the second sentence. So both the two sentences, they have different meaning, right? But in the bag-of-words model, because we only count the frequency of each word. So in the bag-of-words model, the two sentences, they have the same representation. Okay. Okay. So but if you want to count the position, the order between words, you can use another way to extract the features from it. Not only count the word frequency. Okay, maybe you can use you can count the two words appears together. For example, like John is, use this as the two words great, and to count how many times it appears. And if you count the two words together, then at the same time you keep the order between the two words. Okay, but we will not address it in today's lecture. Okay, we just keep simple, only consider the bag-of-words model to count the frequency of each word. And there is another frequency called the document frequency. So the document frequency is to measure the number of documents in a collection that the term occurs. So the idea is, if these terms appear in many documents, so its document frequency will be high. So it means the words is maybe is less informative. Okay, if the words appears just in a few documents, maybe it means the words is more important. It contains some meaningful. It's very special. So So based on this intuition, we develop an inverse document frequency to factor such a document frequency here. Okay, let me give you an example. The document frequency is constant. It can be represented here. Show you some two words: the insurance and the try. Okay, so if we count, given a correction, we count how many documents contain this word for insurance. Okay, here you see the document frequency is it's about 4,000 documents. So it means about close to 4,000 documents contain this word. And for another word, try, there are about more than 8,000 documents contain this word, try. Okay, so for these two words, which word you think is meaningful? Is more meaningful? Insurance, right? If the document appear this word, this means I think it's related to insurance, related to financial, related to money, right? But if the word contain try, it means what? It's still ambiguous, right? We don't know what is the main concept the document want to address. We don't have any idea. Because try is just like a verb, okay, and you can try to, you can use it in any areas, in any topics. So you don't have a very clear idea about this document. So this reflects a fact that if your document frequency is lower, it should be more meaningful. Okay, so we should give it a higher weight to this word. So that's why we call this inverse document frequency here. Inverse document frequency to factor the weight of the term. Okay. And in this slide, there's another term called a correction frequency. Now, correction frequency is different from the document frequency. You try to count a term of the number of the token of the term in the correction, the total time it appears in the whole correction. Okay, so for the interest and try to use the example again, is correction frequency is more than 10,000, and for try is also more than 10,000. So this means that correction frequency, this word appear in the correction, appears so many times. They have a similar times, similar close frequency. So this means the correction frequency may not can well reflect the importance of these words. Okay, so through some statistics and some inspection, we find document frequency is better to reflect the importance of a word than using correction frequency. Okay, so any problems? Okay, so now we introduce the term called TF-IDF. Okay, we have shown it in the previous slides. So a traditional IR system, we can use the TF-IDF to compute the relevant scope between a document and a query. Okay, so here the TF-IDF is calculated like this. So the TF means the term frequency, and the IDF means the inverse document frequency. Okay, so we can use the two weights to generate a joint weighting. Here you can see the TF, we use a log because term frequency usually very large. Okay, so here we use a log to make this scale smaller, and the time with inverse document frequency here. So you see the TF is in the is a denominator here. Okay, so it's inverse. If it's large, this means the weight here in this term will be, the importance will be getting smaller. Okay, so here is formulated as an inverse document frequency. We just just get the two terms multiplication together, get the final weight for the word in the document. Okay, so this equation is widely used in information retrieval for decades. But now we have a new technique, use the deep learning we can capture a beta relation to model the weight of a word by using deep learning. Okay, now so your matrix can be expressed in a new form like this. Okay, now this each entry now is to represent the TF ideal weight. Okay, so you can see the entry. So for this is for the anthem. For this term, the importance in this document is 5.25. And for each document, for each plate, okay, you can see the first column is to represent a document vector. Okay, so for each document, you can see you can represent it as a vector like this. So it's what we call a vector space. Okay, so actually the ranked documents is work in a vector space. So now with this TF-IDF, we turn it, all the document is represented as a real valued vector. Okay, any problems? Okay, so it's natural to use a vector space model when you present your queries and the documents into n-dimensional vectors. And we can compute the query and the documents, the similarity, by using some measurement. For example, like the cosine similarity. Okay, if the two vectors, you can compute their cosine similarity, or to compute the Euclidean distance. It's a two general way to compute the similarity. Okay, use it to reflect the relevance between the two vectors. Okay, here is a summary. Okay, for ranked retrieval in vector space, we will represent the query in documents as a vectors. And the vectors is actually to be represented in a TF-IDF form, or just use some text encoders to transform your document into a vector. And we can, when they are represented as vectors, we can use cosine similarity or Euclidean distance to calculate their relevant scores. Then we can rank according to their scores and retrieve the top K documents to the user. Okay, any questions? This slide introduces another ranking function. It's called a copy BN25. It's a well-known measure to calculate the scores between the document and your query. Okay, so here we show it's also use the IDF inverse document frequency, and the term frequency is a function f. It represent the term frequency. Okay, so by using these equations, is IDF's inverse document frequency is calculated here like this. Here the n is the total number of the documents in your data set, and the n of Qi is your document frequency here. Okay, so you see it's the inverse, right? Use the minus to represent the document frequency in the inverse form. Okay, so it's the inverse document frequency here, time with your term frequency. The function f is represent your term frequency for a given query and the document. Okay, so it's called BN25. Any problems? It's a well-known. It's already widely used in many benchmarks. So if you read some information retrieval papers, sometimes you will see they take it as a benchmark to compare with the performance. Okay, so another system is also work in the vector space, but now we start to use the deep learning. So it's called there's a very famous paper called Word to Vector. It's published in ICLR, so 10 years ago. Okay, the paper is called Efficient Estimation of Words Representations in Vector Space. And you can treat it as an initiative of using the deep learning in NLP, in natural language processing. Okay, like a pioneer paper. So in this paper, they try to learn the word embeddings from the database. Okay, here they propose two learning methods. One is a continuous bag of words model. Okay, the next is a continuous skip word model. These figures is copied from their paper. Okay, so the left-hand side is a continuous bag of words model. Okay, so by using this model, so here they will give an input. You can see the input. I have 4 words here. I want to use these 4 words to predict this middle word. Okay, so it's called CBOW, bag of words model. Okay, so I will use the first 2 words, or I should say token. First 2 tokens and the next 2 tokens to predict the middle word. Okay, so we can use the first 2 tokens, use their representation, and the next 2 tokens representation sum together to predict your middle word, the teeth token. So this is the first model, CBOW. The second model is called skip grade. Skip grade is I use this teeth token to predict this surrounding tokens. Okay, so here I can use this word to predict its previous word and the next word. It's called skip grade model. Okay, in their papers, they just demonstrate the 2 models and then compare which one is better. So maybe you can guess which one is better. I will give you an answer. You can pick which one you think will be, after the training, which one will be better. This model tries to use 4 words to predict the middle word. And this model tries to use only 1 word to predict the surrounding 4 words. So in their experiment, using first one.
For the efficient, for the speed. For the efficient, the first one.
For efficient?
Yeah.
Yeah. For
like
yeah, maybe because it
nearest
provides
results.
Yeah. Yeah, but how about the accuracy? Which one you think is more accurate? How do you think? You have an answer?
Something.
Yeah. Okay. You just tell us your answer. Which one you think is better?
Right side.
Right side is skip grade. Why?
Because I'm just guessing.
No reason. Okay, based on your intuition.
Yeah.
Okay, so in their experiment, skip grade gets a better result than the continuous bag of words model. Because they think, in their paper they say, they guess. Based on this, if you just use a little information, just a few information to train your model, so you make your model stronger. Yeah. So they just give this conclusion. So just according to the results, they give such a conclusion. Yeah. Okay, so it means if maybe you don't need to provide rich information, and you can still make your network to be trained even better. Yeah, sometimes. And what is the skip grade? Okay, here I show you the examples. You can imagine that in the skip grade there's a sliding window to slide the sentence. Okay, suppose your window size is 2. Okay, here I will use the middle word as your anchor and try to extract your surrounding word as your skip grade feature. Here the Y is your anchor and the window size is 5. Okay, so I will get is previous token and the next tokens. Okay, and then to generate your skip grade like this. So Y in the left. Just take any word in the window, pair with your anchor text, anchor words here. So the Y and the left is your first skip grade, and the Y and the load is the second. And the Y and the shimmer is the third. Okay, so we generate a skip grade for the anchor word Y. And then we shift your sliding window. Okay, now here the shimmer is your anchor word. So we based on this to generate this skip grade in this way. Okay, you can see shimmer Y and the shimmer low, shimmer the in, shimmer the low. Okay, you get the 4 skip grades. Okay, so it's the last window you can get the following 2 skip grades. Okay, any comments? Okay, if your window size is 3, so you have to expand to generate, you will generate more skip grades like this. Here, if your anchor word is shimmer, okay, your first 3 tokens and the last 3 tokens, they will pair together with shimmer to generate your skip grades. Okay, any problems? Okay, later we will use this skip grade to we will use the anchor word as your input and this paired word as output. We use it to do the prediction. Okay, in this work, in the word-to-vector, in this test, they hope after their training, these words can keep the semantic and the syntactic relationship between them. You see, here we show the 2 pairs of 2 pairs. So one is the woman and the man, and the other pairs is the queen and the king. And their relation can be modeled in the vector space by using the Euclidean distance. So the distance from the woman to man should be the same as the queen to the king. We call it the semantic relationship. It should be close. Okay, another example is the syntactic relationship, or like the big to the biggest. And this is the small to the smallest. So the relation between the 2 pairs should be, their distance should be the same. Okay, so that's what we call to keep the relationship according to the semantic or syntactic. So I hope after their word-to-vector training, they can make all the vector embeddings. They already keep these relationships. Okay, so suppose we use the example to calculate their relations. Here, I use the positive, like the positive pairs, like king and the woman, and the negative means man. This equation can be formulated like this: king minus man plus woman, and the result should be queen. Okay, do you agree? Okay, so let's calculate after the training. The king's vector embedding is like this. It's king, and this is the man, and this is woman. So we perform a calculation like king minus man plus woman, and their embedding vector will be like this. And compare with queen. This is the trend embedding for queen. So you see that are they similar? Somewhat similar, right? Okay, so this is what they want. They hope through some calculation between words, and the calculation is actually to calculate their embedding vectors. So in the vector space, you can do the calculation, right? And then the calculation, the result can be used to reflect their relation, their similarity, and something else. Okay, here is a training process. So give your training data set here. Okay, I have input words and output words. Okay, all these are from your scapegrace. Okay, your scapegrace, we have an anchor and the surrounding word, right? Like this. Okay, so you have input word and output words. And I give the target. Target means if these pairs appear in the scapegrace, I will give the label 1. Otherwise, the label will be 0. Okay, so this is our training data set. And the model will use 2 matrices. One is your embedding. Okay, so for each word, each row represents a word's embedding. As the first word's embedding, the first row, and the second row is the second word's embedding. Okay, you have all of your dictionary's words. Okay, show in your embedding matrix. And is another matrix called context. Context also lists all the words in your dictionary. And here each row represents the words embedding. The 2 matrices can be different. Okay. It's just initial by some random matrix first, but after training they will be stable. Okay, in the training, so our input word and output word, and we also give you a target. So give your input words in your embedding matrix, and is in your another context matrix. We use different color to represent the 2 matrices. Okay, so your input word here not, and you compute your output word in another matrix here. So you can see the result, the input and the output, their inner product. We can compute their score like this. But compare with your target, you see your prediction and your target, they can throw some activation function. You can calculate the error between your prediction and your target. And we use this error to feedback. It's a back propagation, a standard way to change your deep learning model. Okay, and you can update the model parameters. So after several iterations, several epochs, okay, now your model is stable. Then when you finish your training, we only use the daily matches and discard the context matches for your inference or in your test stage. Okay, so any problems? Okay, so next is a transformer. So I believe everybody have heard the transformer, the transformer model, right? So here I just recap you some details in this model. Okay, this paper published by Google. Attention is all you need in NIPS 2017. Okay, so it's 8 years ago paper, but now it's very popular. Now becomes a standard in all the models to do like the LLM, all the ChatGPT or the Llama or the DeepSeek. They all use transformer as your basic prompt to train the model, and even for in addition for some computer vision and in some other areas, they all use a transformer to train the model to do the image, to do the computer vision test. So it's very popular. It's now become a standard, a commercial and academic standard in the world. Okay, so it's the first sequence transduction models. Just use the attention mechanism, and we try to address the problem that if in a traditional model to deal with the sequence-to-sequence learning, okay, they have problems if they use the recurrence like the RNN model, recurrence neural network models, or LSTM models, it's called a recurrence model. Or use the convolution model like the CNN, convolutional neural networks. Okay, they have a problem for their speed, for their efficiency. They are not easy to do generalizations in training. And transformer is to make the whole process can be parallelized, and the multi-headed self-attentions. It can pay attention globally for the whole your tokens at the same time, so that to make the process to be very efficient. And this is the basic framework architecture for the sequence-to-sequence architecture. So in this architecture, you can see here we perform a test called a translation using RNN. Okay, so you see it's the encoder and the decoder architecture here. So basically, for the sequence-to-sequence, I give you the input here. I love you. And all you should turn is when input to another model here. And I will use this input to generate a representation Z. And based on the representation Z, I will output my translation result. Here I translate the English to Chinese. Okay, so if you know the Chinese word, okay, so you can see each word just compare with the Chinese word. It's like this. So this part we call the decoder. Decoder here. Okay, so such a sequence-to-sequence architectures can be expressed. We can use the equation to express this idea. So if you input the word x1 to xn, and I hope to find the probability to generate the y1 to yn. You can think I give you n tokens as an input. Given the condition, I will estimate the probability to generate y1 to yn tokens. And this probability can be calculated in this way. The first term is given the input, the probability to generate the representation Z here, and the times with these probabilities for each token. Okay, so it's also represented as autoregressive. Okay, so if I want to predict the probability for the T token, I will use the probability from the first token until T minus 1 tokens, and also with Z, with this condition to predict the probability to generate the T token. Okay, it's called autoregressive. Okay, so that's why you see the generative model like the GPT, they will generate the word one by one, right? They will generate all at the same time, just generate one by one, because it also makes sense because we write this word one by one, right? Like this, so it's try to imitate the other people we are writing our sentence. Okay, so this is the traditional sequence-to-sequence model by using RNN. Okay, but RNN has a problem because if you process it in RNN, each RNN keeps a memory of the previous state. So it means, given you the input here, you have to process 1 and 2 and 3. You have to follow the step. You cannot process all at the same time. So it's make a bottleneck to process, to make it more efficient. But later in the transformer, they can process. They will attend. They use the attention mechanism, so that they can attend all the tokens at the same time. So also you can make your encoder more efficient. But in the decoder, they also have a very clever. Although you have to generate the word one by one, but they have a very clever idea. They use the masked attention, so that you can attend all the tokens at the same time. But I use the masking mechanism, so to make your training is correct, following the autoregressive way. Okay, so in the transformer, it also follows the encoder-decoder structure, and your encoder sequence, you encode the sequence from S1 to Sn to represent to a representation Z, and then you decode the representation Z to generate your output sequence Y1 to Yn. Okay, it's the same for the previous slides. Okay, and here they formulate autoregressive. The idea is you will consume the previous generated symbols, okay, as an additional input to generate the next token. And the attention model, because it can attend all the tokens at the same time, so it's easy to be parallelized. Okay, this figure is copied from the original paper. Okay, so first I want to show you the flow of the encoder-decoder. Okay, the left part is your encoder here. Okay, give you the input, slow embedding, and with some position embedding, and then we perform the attention mechanism here, and so some basic blocks. Okay, so it's the encoder part. Then for your output part, all your output data will slow the embedding and also to multi-head attention. But note that here we use the masking, not the same. It's a little different here. Okay, we use the masking multi-head attention here, and then It's another multi-head attention. It's called a closed attention because in here the attention will attend to the output from a representation from your encoder here. So your input representation will input to here to do a close attention with your output token. And then we just repeat it several times. You see here is N. N means we will repeat the block several times. So here in the paper they say N is 6. Okay, so after this several times, then finally you will output your probability to predict the next tokens. Okay, then I will choose the highest probability. Okay, to be your, we can calculate the loss and the fit to your, continue to your, calculate your next output. Okay, so it's a general flow of the encoder decoder. So, any problems? Okay, so next is the masking multi-head attention. So the masking is trying to, it can ensure the auto-regression works. Okay, the idea is because in your original attentions, actually you can see the all tokens at the same time. Okay, so for example, give you I'll give you a small case for your, so first for your encoders, what's the attention matrix looks like. So I use the example like it's I. Can you read these characters? Okay. Okay, it's my query. It's called a Q, and they already embedded into a vector representation. Okay, and here is another. So it's called a K. It's called a key. Okay, this is called a query. We call it a self-attention in encoder. In encoder part, this is the self-attention because we will attend ourselves. Okay, we will see. Okay, it's our query, and also they serve them as a key. So I will compute their similarity. Okay, so you can imagine that there's a matrix here. Okay, this we call it the attention matrix. Okay, here we compute the similarity between each tokens, between the query and the key. Okay, note that the representation in query and in key can be different. Okay, but so we can compute the similarity here. Okay, between I and the and U. Compute the similarity by just using inner product. Okay, so you calculate all the scores, like the weights between all of them. Okay, so it's called a self-attention. Okay, we apply it in our encoder here. Okay, but how about decoder? In decoder, they work in a different way. Remember, they should be processed in an auto-regression way, right? So in your decoder should be like this. Sorry, I forget to it. And here each is we call it importance between the two. Okay, between your query and the key, we calculate the importance by using an inner product. And for this importance, here is another matrix. It's called your values. Okay, this is the value matrix. The value matrix represents, here we have three values vectors. This one is your I, is the love, is you. I have the three matrices, three vectors representing the value matrix. Okay, so this is the first row represent the first token, the second row, the third row. Okay. So based on your importance, we calculate in our attention matrix. Okay, we can just to generate a new representation for the token I. So the calculation, I will show the equation later, but the calculation is simple. Just compute do the matrix multiplication between them. So for your first token I, the i's new value we can write as this. The i's new representation can be represented by using the we call it relevance between 1 attention expression. So A11 means this one times with the matrix times with your value matrix. Okay, so I just use this to time with this. Okay, I can generate a new vectors. Okay, so this means I suppose this the attention value here is 0.7 and this is 0.1. Okay, after the softmax, we generate a probability between the query I to the three key tokens. Okay, we have get the following weights, and then we just time with your value matrix, and this means the i's matrix I will get, I will receive I will receive 0.7 from here, and okay, and we just sum together to generate your new representation for the token I. Okay, it's called attention. Okay, so this is the whole step for whole calculation. I will show the equation next slide, but it's a whole calculation for attention mechanism. Okay, so it's for encoder, which we do this way. For decoder, we also did it similar, but with some modification. In decoder, you remember that we have to do it one token first, then next token, then the third, then the second token, then the third token, right? So in your decoders, so again, we have okay, I have in my decoders actually I will use my result as the output. Okay. So okay, so here you see in our output we already know the correct answer for I love you, right? The translation for I love you is 我爱你, the Chinese word, right? So in output, I already know your correct answer, right? During the training, I know the ground truth. Okay, so I use this as I apply the same idea again. Here, this is the query. This is the query. And here is your key. Okay, so I use it to do the self-attention here. Okay, so then I calculate all the attention matrix, all the entries with their relation. Okay, but I have to put a masking here. Yeah, because when I do the encoding, each time when I use 我, a Chinese word, because it means I. It means I. It means love. It means you. Okay, when I generate the Chinese characters, okay, I will use 我. Okay, I will attend 我. But can I use the information for I and me? Can't, because they are after your first word, so you cannot use the information. You cannot use the information here. You cannot use here. Okay, so the same philosophy. So if you want to generate I, you cannot use its next token, so you cannot use it. Okay, so that's why they call it masked attention, because you follow the same way to calculate the query and the key's relevance scope. But when you apply in the encoder to do the self-attention, okay, you cannot use your next token's information, so you just make them to be 0. So after you calculate, it's like solution max. You should only get the result here. For example, the probability after the softmax it become 1, and the others should be max to be 0 here. Sorry, I should. It should be 0, 0, 0 here. Others maybe I just keep sorry. Maybe like this. Okay, so all these are masked to be 0 to make sure your attention is in a auto-regressive way. Okay, any problems? Okay. Okay, so I just go through it quickly. Sorry, I know the time is already due. Okay, the next is a feed-forward. You can see a feed-forward block here. The feed-forward is modeled as this. It's just use one linear layer and the second linear layer here. And with the max is a remove activation function here. Okay, so each feed-forward is represented and 2 linear layers with a remove activation function. And for your input-output embedding here the input is embedded by embedded, any token is embedded to 512 dimensions, and the plus with the position encodings. The position encoding is modeled in these two equations. It's based on your position and then your dimension. Okay, you give the different this equation to encode, give a spatial position encoding. So just plus with your input here. And finally is to the regularization. Okay, because they try to combat the overfitting problems, so they apply the dropout and the label smoothing. Okay, label smoothing make your label smooth, not only 0 and 1. You can use 1 as a 0 point, very small probabilities, not just 0. Okay, to make your label smooth. Okay. I think it's a general review of the system architecture. Okay. Okay, sorry, the time's up. Sorry for taking your time. Okay, thank you. 哎，你们要关投影机吗？就他们要
没有，他不用。
不用，
他们说
他们只要上课是不是？哦。